we can. Great. Okay, so we'll start immediately. Our next speaker is David Pereñiguez, who will talk about quasi-normal modes in ADS NAT black branes. So please go ahead.
Okay, so thank you very much, and thank you very much to the organizers for putting this nice conference together. It's very nice to be presenting my work here. So this talk is about quasi-normal modes of ADS black branes with NAT charge, and it's based on this paper I published together with Pablo Cano, who's at Leuven at the moment. So to begin, let me just remind briefly what is the role of black holes in the ADS CFT correspondence. So roughly, black holes are believed to be dual to quark-gluon plasmas in the boundary. The temperature of the black hole determines the temperature of the dual QFT. The Euclidean partition function corresponds to the partition function of the finite temperature theory in the boundary, and so on. In particular, black holes can be used to probe thermal theories in the boundary. And we know, for instance, that the entanglement entropy in the boundary corresponds to the area of minimal surfaces. Complexity in the boundaries can be evaluated by computing the action in the Wheeler-DeWitt patch. But here we are particularly interested in what concerns hydrodynamics and correlation functions in the boundary, because these are dual to black hole perturbations in the bulk. So since we are going to be talking about perturbations in the bulk, I should define briefly what quasi-normal modes in ADS are. So they are linear fluctuations of fields that, here I keep generic, so this capital psi corresponds to a generic field, subject to some particular boundary conditions. So the first boundary condition is that they must be regular at the horizon. And this physically corresponds to having only ingoing waves, so waves that go through the horizon, but not propagate along it or escape. Those modes would not be regular. But at infinity, and unlike flat space, we don't have boundary and we don't have plane waves because the ADS potential acts as a confining potential, right? So the two independent modes at infinity are this decaying mode, the normalizable mode, and this other mode that goes as R square. Yeah, so these are the two independent solutions. Both of them can be interpreted holographically. So the term that goes with R square corresponds to or encodes the effect of an external source that we are inducing on the boundary from the bulk perturbation, while the mode that decays with R, so the normalizable mode, encodes the expected value of the dual operator of the fluctuation of the bulk fluctuation. So the paradigmatic example is a gravitational fluctuation that couples at infinity with the energy momentum tensor of the theory in the boundary. So what are quasi-normal modes? Quasi-normal modes are those fluctuations for which those fluctuations that do not induce an external current at the boundary, so that they have no non-renormalizable mode, right? So the only mode that we have at infinity is this decaying one. So we are still allowing the energy momentum tensor of the dual theory to fluctuate, but not inducing an external current. This is the definition of quasi-normal modes in anti-de Sitter space. Once we have imposed these boundary conditions, in particular the one at infinity, then the problem actually becomes overdetermined. So it becomes a characteristic value problem for the frequencies. This means that there will only exist a discrete set of solutions for the frequencies at which the field fluctuations can exist. So with these two conditions, then quasi-normal modes describe linear responses in the dual plasma. And for instance, the quasi-normal frequencies correspond to poles of the retarded thermal correlators. And for instance, well, using the fluctuations of the metric in the bulk or of the Maxwell vector, we can obtain, for instance, transport coefficients associated to the stress energy tensor at the boundary, and so on. All of this lives in the context of holographic hydrodynamics that has been established for a long time and in which a lot of people have worked. So the most studied example corresponds to black holes in ADS5 because the boundary of those spaces is just Minkowski, and therefore the black holes are dual to CFTs evolving in Minkowski space, and for this reason has been probably the most studied example. But there are also other. But in the case of ADS4, there has also been some work in the past. And quasi-normal modes, for instance, have been computed for spherical black holes, planar black holes, and also Kerr ADS black holes. However, there is a case that remains unexplored, and it's that includes the NUT charge. So let me introduce what are these NUT charge spaces. So there was a paper by Misner talking about these spaces, and the title of the paper was Taub-NUT space as an example to almost anything, which suggests that the spacetimes have these spacetime have very particular properties, very peculiar properties. So the metric looks, as you can see here, where the NUT charge is this parameter n. So the Euclidean sections of these spacetimes are interesting for holography because they describe CFTs on squashed spheres, and a lot of people have worked on this. But the Lorentzian signature, which is the one I'm plotting here, like the one I'm showing here, are seemingly pathological. For instance, they include closed causal curves. For instance, del phi becomes time lag at some point. Also, there are Misner string singularities at the poles of the spheres at theta 0 and theta pi, and there seem to be no first law of thermodynamics for these black holes, so this equation doesn't hold. However, recently there have been a series of observations that pointed towards the fact that actually Lorentzian and Taub-NUT spacetimes can make sense, and let's say a program towards a rehabilitation of Lorentzian and Taub-NUT spaces has started recently. And some of the observations that led to the initiation of this program are the fact that, for instance, although there are closed time-like curves, there are no closed time-like geodesics. Free-falling observers do not observe the Misner string singularities. Also recently, regarding the thermodynamics, it was understood that if the NUT charge is regarded really as a charge in the thermodynamical sense, then one recovers a nice first law, in which the entropy is just the Bekenstein-Hawking entropy. And finally, holographically, it's been also possible to provide to make some sense out of these Lorentzian solutions by interpreting the NUT charge as some vorticity, and also studying the fluctuations of scalars and how they interact with the Misner string. So what is our contribution actually to this program? So our work is the first work on gravitational fluctuations of a NUT charge spacetime. And we aim to answer two questions mainly. First, whether Taub-NUT spacetimes are stable. And second, what is the holographic interpretations of that, which potentially consists of some hydrodynamics evolving in an exotic boundary metric spacetime. So these questions will be approached not for the spherical Taub-NUT case, but for the planar one. So we have a black brane. And now let me introduce this spacetime more precisely. So the metric looks, as you can see here, the parameters that define it are the NUT charge and the radius of the horizon R plus, and well, the ADS length. It exhibits two obvious scaling vectors, the del t and del y, while x is definitely not an isometry. Some important geometric properties of this spacetime that we'll be using for perturbation theory mainly is that it is a Petrov type D space. We'll see what that means shortly. Since we are considering the planar case, there are no Misner string singularities in this case. Surfaces of constant R are homogeneous, so this solution is of a Gödel type. And also there are several killing horizons, not only the one associated to the proper horizon, but there are also other ones due to the fact that this space still contains closed causal curves, although it doesn't contain closed causal geodesics. So thermodynamically, the temperature is given by this equation that you can see here. And if we plot it for fixed n, we get a plot of this form, which looks like Schwarzschild ADS, but is actually pretty different. And the reason is for a fixed temperature, we have two possible solutions, a small one and a large one. But the large one is always the dominant saddle. And in particular, the small one does not even have an Euclidean section defined. So we will restrict in our work, we will mainly consider this branch, the dominant saddles. And this corresponds to considering always NUT charges that are smaller than the radius of the horizon. Okay. So what is the metric of the boundary? So it looks like this. And you can see it's not a three-dimensional Minkowski space. It fails to be so by this factor here. Mathematically, it's just the group manifold of Heisenberg's group, and it's the Lorentzian continuation of a nil space. But by looking at the metric at the boundary, we can already guess that the boundary theory will be characterized by the temperature and this parameter here that we still don't know how to interpret. But I can already say that it admits a neat interpretation as a background magnetic field in the boundary. So finally, it will be very convenient to introduce what is known as a Newman-Penrose frame associated to this solution for the approach to perturbation theory we are going to be following. What is a Newman-Penrose frame? So it is roughly just a frame in the complexified tangent space. It is composed of a real null vector K, real null vector L, and a complex null vector M, so that K, L, M, and M star form a basis. So here, K and L are geodesic and shear-free generators of geodesic congruences. This means that they are principal null directions of the Weyl tensor by the Goldberg-Sachs theorem, and we will see shortly why this is important. But you can think of K and L as ingoing and outgoing radial null geodesics. Okay, and this is like the intuitive picture. Also, they are chosen so as to be parallelly propagated, like the whole frame is parallelly propagated along K. And the reason why the fact that they are principal null directions is important is because we will be following the Newman-Penrose formalism for perturbation theory. So in this formalism, one decomposes all the tensors of the theory, for instance, the Weyl tensor, into their components, their independent components in the Newman-Penrose frame, this KLM. For instance, the Weyl tensor is completely codified in 5 independent complex components, phi0, phi1, phi2, phi3, and phi4. And the fact that this space is of Petrov type D and that K and L are principal null directions makes 4 out of the 5 Weyl scalars vanish. Okay, so the space-time is very neutral gravitationally, let's say. This will simplify a lot the equations of motion when we linearize the theory and leads to the master equations we'll be using. Okay, so only one component of the Weyl and from 0, slope length of the horizon. And as we said, in order to keep ourselves in the dominant saddle solution, we need this parameter to be smaller than 1. Okay. So regarding the approach, we'll be following perturbation theory. As I said, it's the Newman-Penrose formalism. And one has decomposed all the tensors in their components in the Newman-Penrose frame. Then the way of obtaining master equations for the gravitational perturbation is as follows. So one, first of all, chooses a frame as we've done, in which most of the quantities vanish, and then computes the linearized Cartan structure equations. And once they are linearized, it is possible to impose Einstein equations on those. And then the equations simplify enough so as to decouple some master equations for the linear fluctuations of the psi0 scalar or psi4 scalar. Okay. Here, these rho, gamma, and mu are just the components in the Newman-Penrose frame of the spin connection. Delta, capital delta, and D are just the names we give to the tetrad vectors when they act on scalar functions. Okay, these are the so-called Teukolsky equations that one can rederive for our particular spacetime. And yeah, he understood this in the 70s and obtained the coupled equations for Kerr. So we here follow roughly the same procedure. So now if we assume that the fluctuations of the Weyl tensor have this form, so they are eigenfunctions of the 2 obvious scaling vectors of the metric, and define some appropriate radial and planar operators, we will see that the equations decouple. Sorry, that the equations separate because they are already decoupled here. But here I would like to drive your attention not so much to the radial operators, which look pretty much like any other Petrov type D space, like the radial operators for any other Petrov type D space. I'd like to drive your attention to the planar operators. These are completely specific of this solution, and we have written them here in this form as A dagger and A, because with this they turn out to realize the Heisenberg algebra. We will see that this actually has a meaning because all the perturbations will be able to organize all the perturbations as Landau levels, as we will see shortly. And this traces back to the fact that these 2 operators exist. So with this, we can just write down a separated solution for the fluctuation of the scalars and write down nice radial and planar equations. So again, before looking at the radial equations, we focus first on the planar ones. If I call momentarily to the frequency, I call it E, and to this combination of the net charge and the ADS length, I call it B. I obtain that the radial equation, the planar equation, looks like this, where Q is a separation constant. So this looks very much like a quantum harmonic oscillator in which the origin of the potential has been shifted. And then in order to guarantee boundedness of these functions at infinity, this Q must be discrete, right? Must be quantized. However, the exact analogy of this equation is not given by an harmonic oscillator, but by what is known as Landau quantization. So exactly the planar equation that we have obtained is identical to the equation of Landau quantization. The Landau quantization is nothing but the quantum mechanical system that one obtains by considering a particle with charge E immersed in a constant magnetic field. No? If one takes this quantum mechanical system and sets the magnetic field to equal to 2m over L square, then the equation for the Hamiltonian evolution becomes exactly the planar equation we have obtained. So we can think actually of this quantized number Q as Landau levels. So now the following point is the boundary conditions that we need to impose on the fluctuation. The holographic boundary conditions, and this is very important, are imposed on the field and not on whatever master variable you use to compute the frequencies, right? So we need to reconstruct the metric perturbation out of the master variable. This is a major problem that involved a lot of work in the 70s, but there was a major breakthrough by Wald in the 78. It is a result that I will not explain in detail here, although I'm writing it down, that roughly tells us how out of a master variable that satisfies some master equation, you can think of it as the Teukolsky variable satisfying Teukolsky equation, although it's not exactly that. One can obtain a solution of the Einstein linearized equations just by hitting. There was a question? No? Okay. One can construct a metric fluctuation just by acting with some specific operator on this master variable, right? This operator can be computed in terms of the Newman-Penrose variables, and well, this is the way of simply recovering the whole metric perturbation out of a master variable. This master variable is known as the Hertz potential. Was introduced by these authors. And well, one can work out the form of these solutions plus this operator in our particular case, and the metric we obtain is this one, right? I'll spare you the details on how to compute each of the things. But the point is that out of a master variable, we have been able to obtain the metric fluctuation. So now we are in conditions of applying the boundary conditions. For that, we introduce some new radial variables that are more amenable for computations. And we can already read off what must be the boundary condition at the horizon, because that one is just regularity or ingoing waves. Okay, at the horizon, these radial functions have to behave like this, where the exponents are given by these two, and these two coefficients. However, asymptotically, we see that the general behavior is given by these constant plus decaying modes. And so one is tempted to say, okay, we kill the non-renormalizable mode A and keep B. But this is just wrong. This is just wrong because, as we said, the boundary condition that we have that makes sense holographically is imposed on the metric. So what we have to do is impose the boundary condition on the metric and then read off what is the boundary condition that our master variable must satisfy. And after that, we will be able to compute the quasi-normal frequencies. And this is a point that has continuously been missed, let's say, in the literature. Dirichlet boundary conditions have been imposed on the master variables, which is wrong. So before imposing boundary conditions, it is interesting to introduce first this parameter that's just the ratio between B and A, where B and A are like the parameters that control the two decays at infinity. And the reason why I include these ones is because they are not independent if both psi0 and psi4, both Teukolsky master variables, come from the same metric perturbation. So the relative normalization must be fixed. Okay, and this is before imposing any boundary condition. The way of obtaining the relation between these two parameters, lambda plus and lambda minus, is in terms of some, let's say, involved identities between the two Teukolsky scalars, psi0 and psi4, that are known as the Teukolsky-Starobinsky identities. As I said, these are differential, fourth-order differential identities between the two variables that are obtained once we impose that they come from the same metric perturbation. And in particular, we obtain we have this relation between radial functions, right? So the radial function of the psi0 fluctuation is related to the radial function of the psi4 fluctuation in this form, where these are differential operators. So this is a fourth order differential identity. From this, evaluating this identity at infinity, one reads off a relation between the lambda plus and lambda minus. So this is a relation that we have already before imposing the boundary conditions. But now we can move on and impose actually boundary conditions in the metric fluctuation. To do so, we first go to a gauge in which the metric has no radial component. So like at the infinity, there is no component like going through the boundary. And after using enough, well, actually after exploiting all gauge symmetry, one can write down the metric at the boundary on this form, where we actually recognize now the decaying and the non-renormalizable mode. So now the physical boundary condition follows by setting this H2 to 0, right? And from this, we get an additional relation between the two lambdas that govern the decay of the master variables at infinity. So we have two different relations between the lambdas. We can solve them exactly. And we arrive at one of the main results of our work, which is the explicit and analytic formula for the boundary condition at infinity of the master variables. We get two classes of boundary condition for both psi0 and psi4. And these two classes of boundary conditions correspond to two distinct polarizations of the gravitational wave. Furthermore, if one takes the case in which there is no net charge, these two polarizations reduce to the standard even and odd polarizations of the planar case. So to recap, we have reduced the problem to solving an ODE with some specific boundary conditions at the horizon at infinity, where at infinity these parameters must be given by this expression in which the frequencies enter. Again, this is overdetermined, so it's a characteristic value problem for omega. So there is a discrete set of frequencies only, which are the quasi-normal frequencies. And I can already introduce them here. So first of all, like the general properties of the frequencies we have obtained are the following. So indeed, we find that they are functions of just the temperature and the net charge. Okay, why can I not? Okay. They are actually homogeneous functions on the temperature and the net charge of degree 1. And these are results that can be obtained already by looking at the equations of motion. And the frequencies are labeled by the Landau level, the polarization, and the overtone, which labels the frequencies like from more damped to less damped. So to present the results, is actually interesting to introduce this parameter chi, which is the ratio between the net charge and the temperature, or in the interpretation from the Landau level quantization, the magnetic field divided by the temperature. And if we restrict to the family of solutions that correspond to the dominant saddles, then this parameter chi takes values between -1 and 1. So just by plotting from -1 and 1, we will see all possible frequencies. By using this variable, the quasi-normal frequencies take this form. So they obviously scale with the temperature, where this omega tilde is just a function of chi, this quotient here. Well, already at this point, it is also interesting to mention the symmetries that these quasi-normal frequencies exhibit. While this one is pretty standard, this actually is a bit less obvious, and actually you cannot see them immediately from the equations of motion. So ordinary quasi-normal modes, we are plotting in particular the lowest overtone, have this form. So here I'm plotting the real and imaginary part of the minus polarization, here the real and imaginary part of the plus polarization. And we can see that the real parts behave as stepwise linear behavior, approximately. while the imaginary parts have a non-monotonic behavior, which seems to be characteristic of systems precisely submerged in constant magnetic fields. However, more interesting than the ordinary quasi-normal modes are a special family of modes that can be related to the more standard hydrodynamic modes in holography. So if one considers a black brane that has the dual theory, so that the dual theory lives in flat space, then there are special kind of modes, which are known as the hydrodynamic modes, which correspond to those that the frequency of which vanish when the momentum of the mode goes to zero. Of course, in our case, the momentum is quantized by the Landau level, so we don't have a continuous momentum. But we find that there is a family of modes that goes to zero as the net charge vanishes, and we call them pseudo-hydrodynamic modes for a reason that will become clear soon. They turn out to exist only for the plus family, and they exist for every value of the Landau level. So we can plot this special mode here. Again, the real part behaves stepwise linearly, and the imaginary part behaves in this non-monotonic way, but they start at frequency equals to zero, as it corresponds to this pseudo-hydrodynamic behavior. Actually, we can make an analytic holographic prediction for the frequency of this mode by considering the large temperature regime. This large temperature regime consists on taking the temperature way larger than the net charge, which corresponds to having a very small chi. And with this, it is possible to obtain an analytic expression for the frequency, where these coefficients AQ and BQ are given here. So in order to gain intuition on what this pseudo-hydrodynamic mode is, we can actually evaluate it in the flat space limit. So in the case in which there is no net charge and we recover a flat black brane in which we have more intuition. So to evaluate this formula in that limit, we need to take n to zero, of course, but then we need to keep the product q times n constant. So we need to send the Landau level to infinity in order to be able to assign an effective momenta to the fluctuation in the after the limit is performed. This is a manipulation which is similar to that one needs to do in order to recover a free particle subject to a quantum harmonic oscillator potential. So after evaluating this frequency in that limit, we obtain a formula of this form, which can be compared to the first principles computation of the sound wave mode of a plasma in flat space, in which we have this prediction. No? The dispersion relation is as follows, where d is the diffusion coefficient. And if we compare these two equations, we actually recover the correct bound for the shear viscosity and the entropy density. So this is a mode that actually corresponds to the real hydrodynamic mode in the planar case. And finally, just briefly, some few remarks on stability of these spacetimes. So for scalar perturbations, it's even possible to prove analytically that spacetime is stable, so there are no unstable modes. And the proof follows just by deriving an integral relation of this form. These are by a pretty standard procedure. So the left-hand side is definitely positive for at least epsilon smaller than 24. So this means that the imaginary part is negative as it corresponds for stable modes. However, for higher spins, there is no analog proof because the frequency enters in non-trivial ways on the equations. But we have performed some detailed numerical analysis that suggests that there is full mode stability of these spacetimes, even when we depart from the family of solutions that correspond to the dominant saddles, which is certainly at least intriguing. So just to conclude, the outlook is that we have studied quasi-normal modes on top of net spaces for the first time, gravitational quasi-normal modes. And we have found that there is, of course, a discrete spectrum, and the spectrum is also labeled by Landau levels. Furthermore, all the modes are stable, and the interpretation from the CFT point of view is that we've got a plasma in this exotic boundary that, although it contains closed time-like curves, since the bulk computations make sense, then so should the theory in the boundary. And finally, we have provided some explicit and definite predictions for the large temperature behavior of this pseudo-hydrodynamic mode. So it would be interesting to compare this this holographic prediction from plasma perturbations of the plasma directly. And future directions, some future directions would be, for instance, studying the overtone structure towards a proof of stability, perhaps, studying fields of other spins, and compare our holographic predictions with direct computations from the boundary theory side. And also a natural extension, of course, is also would be to consider the spherical tau math space and try to understand from an holographic point of view as well what is the interplay with the Misner string. So that's it. Thank you very much.
Okay, thank you, David. Thank you very much.